All right, I wanted to show you a couple more ways of looking at this little puzzle. Given the velocity curve like this for some motion, what's the position? All right, so another way to do this is to look at this graph, make sure I look carefully and I see that this is +1. So you have to realize, again, that that's not 1 right here. That's +1/2 meter per second. And down here, that's supposed to go there, is -1/2 meter per second. I notice that the velocity is 0, so if I start, remember it doesn't tell me position, so you could start anywhere, but if I'm given that I'm starting here at 1 meter, then until 3 seconds, that's flat. And now I've got V is 1/2 a meter per second. That means that the slope is 1/2 a meter per second. So another way of doing it is to go, I'm going to go from here to here is 1 second. I'm going to go up 1/2 a meter. Now, excuse me for a second while I do, okay, yeah. So this is a little bit, maybe I should have stretched this out. Let me stretch that out. We don't need to do that. I'm going to go here to 1, 2, 3. I think that'll work. So in 1 second, I'm going to go up 1/2 a meter. In another second, which is not here, but it's here, in 1 second, I go up 1/2 a meter, and in another second, I go up 1/2 a meter. Which is to say the slope is 1/2 over 1, up 1/2, up 1/2 over 1, up 1/2 over 1, up 1/2 over 1, and then the negative of that's going to bring me down, lining that up to the same place, and you can think that through. So that's one way to do it. Another way to do this is to look at the area. So I want to talk about that. Remember that graphical area is an integral of this times a change in this. So on this, we've got the graphical area of this earlier to later. Meters per second times second is meter. It's not x, it's delta x earlier to later. And so that's the graphical area in here. If I calculate that, because it's a nice shape, I don't need an integral, I can say that is, looking down here, 3 seconds times 1/2 a meter per second. That delta x is that times that is 3/2 of a meter. I had 1/2 of a meter per second times 3 seconds is 3/2 of a meter. That's my change in position. If I start at 1, in those 3 seconds I will go up 1/2, 2/2, 3/2 of a meter in 3 seconds. And that gives me that right there too. So that's another way to look at it. Looking at that area. And again, if I look at that area, delta x here, it's negative, meaning I can do the same calculation, 3 seconds, negative 1/2 meter per second. So I get a negative 3/2, which is going to be dropping down. My delta x, that's delta x, is going to be a negative 3/2 of a meter. So I think that's interesting to see it all these different ways. We're looking at points, slopes, and graphical area and tying it to the meaning. And we're also looking at this way of writing it algebraically. Let's go over here and take a look at this idea of graphical area also real quick. But you know that if you walk at a certain velocity and you keep that certain velocity or drive for a certain time interval, you'll go a certain distance. And suppose you say, hey, I want to go farther in the same time. What do? Well, you grow faster. So if I go this speed for that same time interval, this is faster, same time interval, and this is slower. How do I see that I've gone farther? Well, as we said, graphical area. This is my delta x going slower, and notice that my graphical area, when I go faster, this increases the graphical area, which is to say it increases my displacement delta x, the entire area. Another way to go farther is to travel the same speed a longer time. Of course, if you think physically, if I travel the same speed but for more time, I'm going to go farther. How is that reflected in the graph? Notice that increasing the time, same speed, increases the area. Or, for the same time, go faster, increases the area. Physically, of course, that makes sense. Faster, same time, farther. Same speed, longer time, farther. Graphical area. And that can be applied to any shape graph. And those are just little bits. One more little piece over here. What does a straight line on a V versus T and a curved line on a V versus T mean? A straight line by a straight line mean either going up here, or it could be going up here, or it could be not as steep here, or it could be going down, or not as steep down, and it doesn't matter where it is. But you have straight lines. You see here that that means that the velocity is changing. The velocity is changing. So this tells me that I've got V is changing. V changes, or changing, at a constant rate, which says A is equal to a constant. Over here, a curved line, whatever it is, I see that the slope is changing on V versus T. The slope is the acceleration. Constant slope, constant acceleration. If, however, I change the meaning on you and make that x, well, now I see that x is changing, but the slope is not A anymore. The slope on this graph is V. I've got a constant velocity, increasing or decreasing my position, constant velocity. That means if the velocity is constant, A is 0. Changing it down here, I see that my slope is changing. So if my slope is changing, then I know that V is not constant and A is not 0. I don't know if A is constant here, depends on how the curve goes. Slope is not constant, V is not constant on this graph. On the other graph, it means something different. So you just have to think about it, practice it enough, and you'll get faster. And I just wanted to show that last thing. Okay, good to go.